Hi, in today's video, we'll learn about one of the most fundamental algorithms in RL called Q-learning. Many modern RL algorithms are inspired from or built directly on top of this algorithm. In this video, I'll introduce this algorithm, give a few examples to explain it, and then we'll talk about parameters and strategies that control the learning process. These parameters and strategies go beyond the scope of this algorithm and will be important in many learning RL algorithms moving forward. So take time and watch over and over if you don't understand. Also, feel free to comment or join our Discord server if you want to take this further. The link to the complete Python implementation is in the description, and in the next video, we'll go over the Python implementation in detail. For now, let's get started with Q-learning.
Q-learning is a foundational model-free off-policy algorithm. In this video, we'll learn about the algorithm and explore how it's model-free and off-policy. In Q-learning, an agent learns the optimal action to take in each state without needing the model of the environment. The goal is simply to maximize cumulative rewards by learning an optimal action value function. Now, to do this, Q-learning relies on the Bellman optimality equation, where the value of a state and action taken is equal to immediate reward plus the discounted best possible future value that we can get. Like I mentioned in the beginning, Q-learning is model-free. This means that we do not need to know the transition probabilities, so we can drop them off and instead estimate the value using tabular Q-learning update, which is represented like this. Let's break this down. Here, QSA is the current estimate of the action value. Now this whole term right here, which is the reward plus discounted Q value, is called the target. We can also see a new term here, which is alpha. This is the learning rate. This determines the importance of new information. We'll talk about this in detail soon. And then we have the discount factor. This sets the importance of future rewards. One additional point to note, if we are in a terminal state, the target becomes equal to reward because this term is 0. This is how it looks in code. To update the Q table, we get the current Q value for the state and action. We estimate the target. If it's a terminal state, the target is just the reward. If it's not, we calculate the target. And then we update the Q table for that state action accordingly. We update the table at every iteration of the learning process. So what's the intuition here? It's that each time an agent takes an action and observes the outcome, it updates its belief how good that action was. And over time, these updates help the action learn the optimal way to act purely through interaction with the environment. Now let's talk about Q value. In Q-learning, we assign Q value to each state action pair. Q value represents the expected discounted reward for taking that specific action in that state and then following the optimal policy. This is very similar to what we do while using the Bellman equation. Here, better actions in a state get assigned higher Q values. Let's look at this example to understand this better. In this example, we look at a lunar lander. We start from a state where the lunar lander is tilted to right at an angle. From here, even though we start from the exact same state, we take different actions in both the scenarios. In scenario 1, our action is that we activate the right thruster of the lunar lander. This corrects its vertical angle. And in scenario 2, our action is to activate the left thruster. This increases the vertical angle of the lunar lander. The resulting state in scenario 1 is that the lunar lander is almost vertical and its angle has been corrected. But in scenario 2, due to the action we took, the angle was made worse and the lander is so tilted that it is almost horizontal now. The probable future result for the first scenario would be that the lunar lander successfully lands and we get a reward of plus 100. But in the second scenario, since our action destabilized the lunar lander, there is a high probability that we crash and we get a reward of negative 100. So the state action pair in scenario 1 will have a higher Q value, and the state action pair in scenario 2 will have a lower Q value. No surprises here. Now let's talk about the key parameters in Q-learning that control the learning process. These parameters are very important and will dictate how good your Q-learning algorithm learns. The first one is learning rate. This determines how aggressively the Q values are updated. You can see from this equation right here, if we have a high learning rate, we are putting more weight onto the target, which means that we are putting more weight onto the future. That means we are learning aggressively. If we have a low learning rate, meaning it's closer to 0, this would mean that we are putting more weight on what we know already, that is the current Q value. High learning rate means we learn faster, so there is faster adaptation, but this can be quite unstable. Low learning rate means the learning process is stable, but it's slower to converge. If the learning rate is too low, we may even never converge. So you can probably guess that we need a good balance of these for the best results. And so a good practice is to start with a high learning rate so that the algorithms learn fast initially and then reduce the learning rate over time. This is learning rate scheduling. This is a common practice across learning algorithms outside of reinforcement learning as well. For visualization purposes, let's look at this plot. Here we have a learning rate scheduler, where in the beginning we start with a very high learning rate, but as the progress goes on, we reduce it. We also set a lower limit for learning rate so it doesn't reduce too much. Now let's talk about discount factor. Since we have talked about it a lot, I will keep it brief here. This balances out short-term versus long-term rewards, or how much we weigh long-term rewards. Typically, in practice, the discount factor is 0.99. This makes sense as we saw from the example of the lunar lander. Future rewards are quite important. And you can see from this simple visualization here, high gamma means you include the future steps. The higher the gamma, the more into the future you are looking. Now let's talk about exploration versus exploitation. This is very important in determining how good your algorithm learns. Exploration is when you try random actions to find better strategies. So when you do this, even if you already know a good action, you explore to see if a better action exists. And exploitation means using only the best action that is currently known to you. Now, although you can get rewards through this, it is still a bad idea initially, because by only doing the current known best action and by stopping exploring, you risk missing the true optimal strategy. So what makes sense is to take an approach called epsilon greedy strategy with a decay. The idea of this approach is to explore early and exploit later. Every time you take an action, you either explore or exploit based on the probability. If you exploit, you choose an action that maximizes the current Q value. But if you explore, you choose a random action. It might be the best action, but it is randomly picked. The purpose of exploitation is to use best actions to gain rewards, while for exploration, it is to discover new paths and improve Q value estimates. This is how it looks in code. It's very simple. You pick a random number between 0 and 1, and if the number is smaller or bigger than your current exploration rate, you will explore, that is, take a random action, or exploit. Now, here also a good optimization strategy would be to use this with a decaying schedule. Initially, you do high exploration, and later, as you have learned more, exploit. So the strategy for ensuring convergence is you should explore sufficiently, because if you don't explore sufficiently, you might never know what's possible. And that is also a good life lesson. Secondly, to reach convergence fast, have a variable learning rate. That is, initially keep a high learning rate and then reduce it over time. This is usually a good strategy for many learning algorithms outside reinforcement learning as well. Then third, you also need to meet the technical convergence condition. This means enough visits to each state action pair. This obviously makes sense because if you want to make sure if a state action pair works or not, you need to visit that pair multiple times to reinforce your belief of whether that state action pair is good or bad. You cannot do this by just visiting a state action pair once or twice. Now let's talk about the Q-learning algorithm itself. These are the practical steps for tabular Q-learning. First is to initialize a Q table. This will have actions and states. I'll show you in a moment what it looks like. Second, we'll update this Q table by looping through the episodes. And at each step of the episode, we observe the current state S, choose an action, execute the action, observe the reward, and transition to next state, update the Q value using the update rule we saw earlier, optionally decay learning rate and epsilon over time, and you have to repeat this until convergence. And third and the last step, once you have converged, you extract the best policy from the Q table. Let's take a look at the first step. So taking the example of this 2x3 grid world that we previously worked with, this is what a Q table will look like initially. All values are 0 initially, and this is the Q table that will update at every iteration. So now this is what the Q learning process looks like in code. Again, it's very simple once you have built all the components. You train for certain episodes, you start with a state, and in a particular episode at every step you take an action. Transition to the next state, get a reward, and then you update the Q values. And then you repeat this. You take an action from the next state, transition to the further next state, and then update the Q value. You keep on doing this until you have converged. After convergence, your Q table will look something like this. For each state action pair, you now have a Q value. And now that you have converged and the Q table is not updating anymore, you can extract the best policy. Now, as humans, we can already see that the best action from the state 0, 0 is right, but we can also see that for taking right action in this state, the Q table has the highest value. Similarly, for 0, 1, right action takes the highest Q value. This also makes sense. And now in this state, we can either go up or right. So these two have the exact same value. And for this one, we go up. And here you can see the action right has a value of -1. So we definitely don't want to take that action. So now after training, our Q table is built and we have extracted the best policy. Now let's talk about why Q-learning is off policy. Q-learning is off policy because it learns the optimal policy regardless of how data was collected. What do I mean by this? The target policy is different from behavior policy because the behavior is based on epsilon greedy strategy. We either take the best action possible or we explore randomly. But updates are based on the best future action, not based on the actual action taken, as you can see from this equation right here. That's why it's an off policy algorithm. Now let's move on to applications of Q-learning. Q-learning was one of the most important breakthroughs in RL, and it has many applications across different fields. Like in robotics, it's good for path planning and adaptive behaviors. In games, it can help us in decision making in dynamic environments. And in resource management, it can be used for scheduling, logistics, and optimization problems. Last but not least, let's talk about its limitations. First, it's not scalable. We saw that we use a Q table. In our case, we had a Q table of size 6 by 4, which was quite small. But I'm sure you can imagine that when there are many states and many possible actions, or in continuous environments where there can be infinitely many actions, this becomes infeasible. Then Q-learning is not applicable anymore, and it's too costly computation-wise. Second, it has poor exploration and can slow down or prevent convergence, especially in big environments. The solution would be to use a deep neural network instead of a Q table. Deep neural networks are very good function approximators. And actually, using a deep neural network instead of a Q table makes this algorithm even more powerful. We will explore deep Q-learning very soon. Next, we'll implement this Q-learning algorithm in Python and solve a grid world.
To find the entire detailed lesson with all the instructions, math, and code, visit our website edreate.com. There you can find everything you see here and much more. Plus, you can find the full code on github.com/edreate. So don't wait around and sign up now at edreate.com.